Hello, my fellow YouTubers. This is Roy back again. Hello, my fellow YouTubers. This is Roy back again. Tonight we're going to talk about torque and angular momentum. And I put it up here so we can watch this a little bit. Be right back. Take you there, drop you off, where you're going to go back. Come on. Huh? So when you get back, We'll just keep the money in your account this time. On the way back, don't worry about it. Yeah, right? Covered? Hey, look at this. I'm filming right now. Through a live stream. I'm making it run electromagnetically. Like wheel with a bunch of magnets on it. It is sick, right? There's people, I got a bunch of people talking about it. I love you. So that's the speed right there. Turn it up. Notice the whole table's vibrating. the speaker out. Holy canola. No, and it's, we're gonna find out why. Let me switch that speaker out. Nothing. I wonder if it has anything to do with I'm turning it horizontally versus vertically. Try another speaker. Too strong. What a beast this is. It's going the opposite way. Well, we were going that way, right? compass is backwards. So let me go ahead and fix the compass. So I know. Hey Vinny, what's up, boo boo? So I know that way is north. The compass is heading towards me north. So you put the North Pole heading towards the compass, and you just swipe across the top of it, and now the compass is reset to Earth's alignment. So right now it's heading north. Hey Dave. So now let's go back. So the magnet's facing out should be north. All right, and before we're showing south. So there's your north. The funny thing is if you go underneath it, the poles swap. So these magnets are north out and south in. There's nothing on either side. In fact, I got 8 more that just came in. And look, these boxes are stuck together only because the magnets are so strong. Look at that. They're not stuck together for tape. It's because the magnets are sticking together. So I got 8 more of these magnets. So in front of the magnets, we're showing north. Underneath them, we're showing south. And above it, we're showing south. Thank you, Dave. Vinny's a good boy. That's the RPM gauge right there. That's the tack. Not the RPM, the tack. Let's spin it the opposite way. That'll slow down on its own. A lot of wobble in here. And the reason I did this because I wanted to do an experiment without having it fixed. Remember we talked about precession and the gyroscopic effect of this wheel? Well, right here, you're already seeing that I have it tied sideways. I'm going to redo this tomorrow to where I can pivot it all the way around, a swivel this way, and then I swivel it this way. So right now you can see that it's wobbling like this. So what we said was use your right hand rule. So the force is that way, and if we take our right hand and look at what's going on here. So the force is that way. The my fingers is the let me see. So we're turning this way. So the force is this way. The torque is that way, and the angular momentum is chasing the torque. So this thing wants to turn itself, depends which way I spin it, wants to turn itself, but it's also, because of angular momentum, it's giving this that effect. So let's go ahead, we're going to flop this the opposite way now. We'll just plug it back in. And now we're just going to start it real slow. Watch it take off on its own. All right. Now it's shaking. And that's that torque and that angular momentum trying to chase each other. So I like to create this wheel here. I like to create this wheel here so it can move around. So whatever twist it wants to take, it can take it. potentiometer is all the way up now. Let's see it take off to its extreme. So I did some calculations today in regards to the Schumann resonance. And let's go over those. All right. So I got a question for you before I read this off. Is that noise in the backdrop? Is it? Can you hear me talking? Clear? Or should I turn the wheel off? Alrighty. So we're going to start off with this. So me start doing the calculations, what I said last night in regards to tapping into the Schumann resonance. You got a question, what is the Schumann resonance? What's going on, William, in the house? So what is the Schumann resonance? So this is my explanation of what we're trying to tap into. And this is why the Schumann resonance comes into play. You guys ready? Are you guys ready? I don't hear you. All right. We're going to start off with the speed of light. The speed of light, guys, get your calculators out. Speed of light is 186,000 miles per second. Write that down. All right, write that down. 186,000 miles per second is the speed of light. The miles around the planet is 24,901 point change miles around the planet. And for you guys, this is a little good cookies to give you. And that's at the equator. Now, they say that the equator is swollen up by 27 miles. So if you were to take the circumference from the poles, from north and south, and take the circumference of the equator is 27 more miles wider than from vertical, up and down. Write that down. And that bulge in the center of the earth is because of the rotation of the earth. Make that a note. Very important. Now, the Schumann resonance. The Schumann resonance, we're going to call this a lightning strike, is a, what I like to call the lightning strike, is a, is a event. It's an event. And that event of the lightning strike is calculated around the whole planet of how many lightning strikes. Before we do the numbers and figure out the Schumann resonance, we're going to talk about lightning strikes, because this is what I want you to look at is my finger. Well, I'm going to bring you over to here. We're going to look at the cross. Now, lightning strikes to me is the event of your striking the ground. Say at the bottom of the cross is the ground. Okay, you guys hear me loud and clear? So when that event happens on the lightning strike, the radiation of that strike goes out horizontally around the whole planet. And that's calculated, the speed of light is 186,000 miles per second. So that's where the circumference of the Earth has the radiation, and I call that the cross, because you have your lightning strike, which is an event, and then you have your radiation, your light goes out from that event and goes around. Now what happens when it goes around? Come on guys, give me some help here. What happens when that strike happens? Think of us as a bell, and the bell is the airspace. Now when that singular event, the lightning strike, happens down the center to the Earth's surface, radiation goes around, hits the same spot, and goes back around again, back around again, back around again, back around again, back around again as a frequency. But it keeps going around until it dissipates. But remember what we're living in. We're living in above the ground. We're living in a radiation, a radial radiation place, to where that horizontal, yes, you got it, Eli. The horizontal part represents the radiation, the electrostatic. The lightning represents the event, the singular event. Now all of a sudden, you start calculating multiple events all around the world. Boom, 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 boom. The radiation is going around. It's going around the whole planet multiple times, so the bell never stops ringing. We keep a frequency. Let's say there's the start of your Schumann. So let's do the math on the Schumann there. Now, we're going to take the circumference of the Earth. We have 24,901 miles. Remember this, speed of light is 186,000 miles per second. You divide that by the circumference of the Earth, which is 25,000. We're going to round it off. 24,901. We're going to round it off to 25,000 per second. That comes out to about 7.8. It comes out to the Schumann resonance. So now you know the factors of the speed of light, the circumference of the Earth, and the lightning strikes that are happening. So if you take our tachometer right now is 3,486. We need to be at 3,700. If you divide the 25,000, divide 186, take 186,000, divided by 25,000, you'll come up with a number. Divide that by 60. So that's how you get your frequency. That comes out to about 7.8 or 7, almost 8.0 in frequency. This is a Pythagorean type of problem here. Pythagoras. So if you look at the revolutions we're doing, and if you divide that number, I don't have a calculator in front of me, if you divide that number of 186,000 divided by 25,000 divided by 60, that number comes out to about 3,700 RPMs, which you divide that by 60, I believe it comes out to about 300 turns per second. I don't have the numbers in front of me or a calculator to give you the exact, but it ties into the Schumann resonance. So basically, let's think about that. What I'm going to do is take my bifilar, and I realized last night in my studies on my video that you can't tap into the bifilar or it disrupts the whole wheel turning. So I'm going to add more wires to my bifilar. I'm going to add one wire that I want to be able, so if I add one more wire, I get two attachments, right? That is going to be to my capacitance. Another wire is going to be to my ground. Another wire is going to be to my antenna. Now, yesterday I said to you guys, ideally what you want is an antenna, a capacitor, a grounding rod, a variable capacitor, and then you want a set frequency. The set frequency would be 3,700 RPMs. That puts us in about 7.8 to 8.0 frequency. We'll be somewhere in the wave. Now, what are we attaching that to? You got to question that. You're going to attach that to a grounding rod, to an antenna. Remember, not only is the Schumann wave a frequency, but you times it by 60, it becomes the speed. You divide it by 60, it becomes the frequency. So we want to hook it up to an antenna. We want to hook it up to the ground. We want to separate it in two plates of a capacitor, and then we want to fine-tune that capacitor with a variable capacitor so we can make a difference in potential. Does this make sense to you guys? I hope so. I believe, like Ed was talking about, that it ain't so much about the wheel or the electromagnetic wave you're putting out. It's the fact that you're creating an electromagnetic wave. It's about tapping in to what's already existing, and how do you do that? And this is, I told you I spent a minute thinking about it. I didn't think much about it, but I woke up this morning with a clear thought in my head of this stuff. So I dug in about lightning, dug in about speed of light, I dug into about the diameter or the circumference of the Earth. And then you could do the calculations there and see it comes down to the frequency of the Schumann resonance. It comes down to the speed of 3,700 RPMs. And I think when it comes down to levitation, one of the parts of the layers of what it takes to levitate does come down to turning a object faster than the planet's turning. Because if the planet's turning at 3,700 RPMs, let's just say, as a number, not saying it is, let's just say that you need to spin something faster than that so gravity doesn't take effect. I'm all about sounds and vibration. That's what these studies are about right now. We could tell certain things that speed not only increases the frequency, I like you guys talking. Keep going. Rock and roll. So one of the notes I've written here is about angular momentum. And you can see here, when you spin, so spin angular momentum is one thing, and it's about the center of the mass, and the orbital angular momentum is the total angular of the object is the sum of the spin and the orbital angular momentum. The orbital angular momentum vector of a particle, where the constant of it depends on both the mass and the particle and the distance from its origin, meaning the top of the rotating and the center of the axial. And what that brought me to is this guy that I drew up this morning, where it's almost like Russellian. It's like a Russell, where if this was the linear plane and the axial and the force you drove down, your expansion comes out like a cone in both ways. And that's where I think what I was just showing you guys with the compass, to where here we're showing its North Pole coming out on the plane, which would be the plane right here. That would be the plane. Then it comes down to a fine point, which would be the torque and the angular momentum. And in this case, it becomes a south up top and a south down bottom. And with that being said, I believe the stuff we don't see is the important thing, because now we're taking this tension and this angular momentum, and the torque is on both sides of the axle of that, and the angular momentum is expanding with speed, expands outward. But the outward is that it's wide, and it comes down to a point. So I think that's where Russellian type of stuff comes in, and where we can utilize that energy there that nobody I know talks about. So what I'm literally talking about, guys, is working with energies we don't even see, but we know they're there based on our empirical data that we have as mankind. That's why I'm doing these videos, get it out there, get a different perspective on it, and get you guys talking about it. Because I'm looking right now, you guys, and you have great comments coming in, you're throwing stuff in there, and that's what it's all about. This is what it takes. It takes everybody. No man is an island. Remember that. What's going on, Tesla? All right, Nick. Call me Roy, Nick. By the way, Nick, I love your comments you're leaving. Remember, no man is an island. Time for pit stop. So, what did we cover tonight? We went over a lot of good stuff, huh, guys? So, we talked about Schumann resonance, what it is, how it works. We talked about we're dealing with radiation emission from lightning strikes, constantly radiating around the whole circumference above the ground to the outer atmosphere, right? We covered that. And the reason I even brought up the cross is because it just, there's a reason it's a cross, and it probably goes deeper than what we're talking about. I'm not bringing religion in. I'm just saying that I always said that it was a vertical, and I can't turn this wheel around right now. But you know, when I just did that test for the first time with the piezo, with the piezo speaker, we got to do one more test with one of the woofer speakers, because I'm throwing out electromagnetic horizontally. I don't know if that is the reason why we couldn't get any sound out of that speaker, but I got a hunch it might be. Because maybe because of the impact of lightning going vertical from up and down, that the magnets would have to be turned this way to react. So we might be out of phase. The magnets might be out of, I don't know. I'm gonna have to go get the speaker right now. Well, let's get that wheel turning again. We're gonna spin it the opposite way this time, and we'll bring that woofer over. And I'm curious. Curious. I guess you can call this damn thing a generator. I was watching some more John Bedini videos today of him, and tell you the truth, he knew you cannot put anything electromagnetic near that wheel. That wheel is not designed to have a electromagnetic load around it. So, which makes sense. We showed that last night. I didn't get to read that whole thing about the tingling of my skin, but that's where it stopped. I'll have to come back and watch that later. Working. It's working. All right. So what do you guys? I'm going to bring this up. Tell me if you can hear it. I think I blew out the piezo. Tell me if you hear this. You guys hear that? Loud and clear? I'll put it over here near the speaker. Look at the wheel reacting. You guys hear that? Cool. Thanks, Anthony. No, Eli. What's a singing stone, Eli? Tell us. $55 hertz? Is it such a stone called a singing stone? Only AC waves turn it that way. These are all north facing out, so I don't know if it's going to turn it. Putting a magnet in my hand, I'm going to see if it spins. Nope. See, with edge wheel, on edge wheel, because the north and south face out, that would spin. Hold on. All right, we're getting spinning now. So you got to be a little distance away from it. All right, so we're going to go back to this thing. So what you're calling collapse the field, Eli, I'm calling a singular event. Because that's what rings the bell. It's all about Mother Nature. The other major part of this is getting the oscilloscope hooked up to the capacitor that's in between the ground and the antenna and seeing what the wave is like, because that wave profile is going to tell us a lot, guys. So I can't wait to get the oscilloscope in the setup, because it'll show us a visual of the Schumann wave, what it looks like, and that's going to be unbelievable. So we have to get it up to 3,700 RPMs. Guess what I'm going to do that? All right, guys. Good conversations tonight. This thing is a mess. When there's smoke, there's fire. Something must be on fire. I can't believe my boy Abraham's lab called it quits. That guy inspired me. Really did. Any of you guys ever watch Abraham's lab? Tesla guy? Well, you might want to see if he's still up before he takes his channel down. He's got a lot of great learning stuff there in regards to frequencies and Tesla stuff. He did a whole bunch of stuff, but that wheel's wobbling pretty good. It does go to show you, though, that the angular momentum wants to drive it elsewhere to where she sits. She's a shaking. I don't know if you can see it shaking so much. Maybe this way you can. See it shaking? That's that angular momentum right there. That's a force in itself that we don't even see due to torque. Peace out, my bro hams. Take care.